Good morning to one and all. Myself Narendra A, lecturer from Government Polytechnic, Chintamani. This is the mine's fourth session which I am using by teaching the strength of materials. In the last session, I have discussed on many problems on this various bars of varying cross sections and analyzing the strains and calculating the Young's modulus and stresses and strains. So that today we will deal with some important concepts. That is, the first one is the strain energy. Strain energy means I already told what is about the meaning of a stresses and strain. Whenever automatically when load is applied on the body, when load is applied in the body, the internal resistance will be developed. So automatically when internal resistance is developed, in the next session what will happen, automatically it undergoes strain also, because every material has a value of an Young's modulus. The every material has an Young's modulus. So that Young's modulus is nothing but it is a combination of stresses and strains. It is a ratio of stresses and strains. Suppose you people are sitting in the bench. If you people are sitting in the bench, so what happens? Resistance will be developed in the bench. That's why you people are sitting. If resistance is not developed, what happens? It undergoes continuous deformation. If undergoes continuous deformation, you people will not able to sit on the bench. So that in the same way, when resistance is developed, you may experience some changes. You may experience some changes. Changes is nothing but you may experience some deflection. So automatically when load is applied, when stress is developed, automatically in the same way, in the same direction, the strain will also develop. So that here, what is the meaning of a strain energy? Here, what is the meaning of a strain energy? Automatically when load is applied, so what happens? Energy will be absorbed by the body. What energy is absorbed means what is the meaning of energy is absorbed means here internal resistance. So that here when body is strained, the energies will be absorbed in the body. The energy absorbed due to straining effect is called as strain energy. Once again I repeat that whenever a body is strained, the energy is absorbed in the body. The energy which is absorbed due to straining effect is called it as a strain energy. So that this straining effect, it may be depends on the type of load we apply, because depending on the type of load we are applying, we have three types of loadings. That is, one is the gradually applied load, and another one is suddenly applied load, another one is impact load. How the energy is absorbing is totally depends on which type of load we are applying. So that we can define that it should be within elastic limit. So within elastic limit, work is stored in the body. So that how much of energy is stored in the body, we can call it as a strain energy. So that by seeing figure we can already explain the stress strain behavior of the for mild steel. Here I showed that within elastic limit. So that working resistance, we can call it as a strain energy or normal energy. So that this energy will be applicable. It is a normal energy, normal loading condition. It totally depends on normal loading condition. So that this is a stress strain diagram here I have shown. That's load versus displacement. So that up to that case, up to elastic limit, we can use this energy. So that what is the meaning of resilience? This is another important term, resilience. Resilience is nothing but it is the total energy stored in the body. Resilience means it is the total energy stored in the body. I already told the meaning of an energy and strain energy. So the total energy developed in the body, the total strain energy stored in the body, we can call it as a resilience. The total strain energy stored in the body, we can call it as a resilience. So why I am studying this total energy and all means, when we apply the load, that should be resisted in the body, so that the total load applying, so that equal resistance must be developed in the body. For an equilibrium case, how much load we are applying, same amount of resistance or same amount of work done should be done in this body, so that time we can say body is in equilibrium. So how much of load we are applying, in the same amount of work done should be done in the body, so that should be equal. If they are not balanced, so that the body is not in equilibrium. How much of work, how much of load we are applying, that should be exactly equal to the work done by the body. So another one is proof resilience. Proof resilience means it's a maximum strain energy stored in the body. See, there are three terms here. One is the strain energy, and another one is the resilience, and another term is proof resilience. Here, proof resilience means it's a maximum strain energy stored in the body. Proof resilience means it can ask in 1 mark or 2 mark questions, definitions of different terms. So that proof resilience means the maximum strain energy stored in a body. The maximum strain energy stored in a body, you can call it as a proof resilience. The maximum strain energy stored in a body is known as proof resilience. So that what we are calculating the strain energy, I already told, this should be within an elastic limit. This should be within an elastic limit. So under one of the important technical term here, modulus of resilience. Modulus of resilience. So what is the meaning of a modulus of resilience? Means we are calculating strain energy or proof resilience. It's a strain energy or maximum strain energy per unit volume. We are limiting this strain energy to the volume, per unit volume. So that modulus of resilience is defined as it is the proof resilience, that is the maximum strain energy per unit volume. Maximum strain energy per unit volume. So this is called modulus of resilience. Just once again I repeat, total strain energy is, it is the work done or energy stored in a body. Energy stored in a body, we can call it as a strain energy. Work stored or energy stored in a body, we can call it as a strain energy. The total strain energy stored in a body, we can call it as a resilience. Strain energy stored in a body, we can call it as a total work done by the body, we can call it as a strain energy. So that total strain energy stored in your body is known as a resilience, and maximum strain energy stored in your body is known as proof resilience. The maximum strain energy stored in your body is known as proof resilience. So modulus of resilience means we are limiting proof resilience of the material per unit volume. Proof resilience per unit volume. And I already mentioned what is the different types of loading. This total strain energy, how strain energy is developing is totally depends on how strain energy is developing, how work done by the body is totally depending on type of loading. How strain energy is totally depends on type of loading. One is gradually applied load, and we can classify into three types. The first one is gradually applied load, second one is suddenly applied load, and third one is impact loading. There are three types of loading conditions, and this is totally depends on how we are applying. This totally depends on how we are applying. So that the first one is the gradually applied load, and second one is suddenly applied load, and another one is impact loading. So the first one is gradually applied load. See, gradually applied means the word itself says that gradually applied loads means we are applying the load. We are applying the load gradually. We are applying the load gradually. That means slow application. That means so that we are applying the loads on the structure gradually. We are applying the loads on the structure gradually. That means step by step. Suppose we are applying. Suppose it's the maximum load taking of the member is 10 kilonewton. Suppose if you take maximum load carrying capacity of the member is 10 kilonewton, we are applying load gradually. That means 1 kilonewton, 2 kilonewton, 3 kilonewton, 4 kilonewton. So that within a less interval, I mean more number of intervals we will take. Suppose I already told, if you take maximum load carrying capacity of the member is 10 kilonewton, we are applying 1 kilonewton, 2 kilonewton, or we are taking at 10 intervals. We are taking at 10 intervals. So that is the meaning of gradual application of load. Suppose I can give an example. If you take a stone of 300 grams, if you take a stone of 300 grams, if slowly if you keep that stone in our head, nothing will happen. If you keep the stone gradually in our head, nothing will happen. That is the meaning of gradual load. Suppose it may totally depends on if you keep the stone on our head, nothing will happen. Suppose if you throw from a distance, if you press suddenly, that same stone, if you press on our head, it becomes more deformations. So that how the gradual load will subjected to stresses. How gradual load will be subjected to stresses. So that here in gradual application of load, in a gradually application of load, here we are equating to the strain energy. Here we are equating to the strain energy. Here how much of load we are applied will be exactly equal to the work done by the body. Here how much strain energy stored in the body is exactly equal to the load applied on the body. So that in the second case, suddenly applied load is nothing but here we are applying the load with lesser number of intervals. Here we are applying the loads with sudden application of load. Less number of intervals. Suddenly applied means we are applying load suddenly. That means I already told, if you take an example, maximum load carrying capacity of a member is 20 kilonewton. We are taking only 2 intervals. Example, we are applying 10 kilonewton and directly we will go to the 20 kilonewton. So here first we are applying 10 kilonewton, then exactly second step we will directly go to the 20 kilonewton. That means that we are applying the load with less number of intervals. In a gradually increasing load, we are taking more number of intervals. In gradually increasing load, we are taking more number of intervals. In second case, in suddenly application of load, we are taking less number of intervals. So that what happens in the strain energy? What happens in strain energy means the effect will be more in suddenly application of load. That means that here work done by the body is more. Because work done by the body. That means the work done is nothing but what? Maximum stress induced. It is a maximum stress induced in the body. So that maximum stress induced in the body is exactly equal to the twice the stress induced when the same load applied gradually. That means that in sudden application of load, more effect will be caused when compared to the gradual application of load. That's very important. If I told in the stone example, if a stone presses on our head very fastly, if you press the stone in our head as a fastly, the effect will be more. If you apply the same stone gradually, nothing will happen. That means that here work done by the body is more. That means that effect caused by the load in sudden application of load is more compared to the gradually applied load. So that another case here in impact loading. Impact itself is that impact loading means impact load usually applies in the traffic. Traffic is in the road, in the design of a bridges and design of a roads. The impact loading is very important. Usually vehicles with move in impact loading we can cause, and usually this load will be applicable in this impact loading condition. So here I will give an example. If a load is dropped to a certain height, from a certain height, so that can call it as an impact. If a load is dropped for a certain height, we can call it as an impact. Here I have shown here one cantilever beam, we are dropping a load for certain height h. See here given another example. So here it is like a cantilever action. Here one end is fixed. And another end is free. Here one end is fixed and another end is free. So in other end we are dropping a collar from top to bottom. See the same, if without dropping, if you take from top to bottom, collar will drop down gradually, slowly. If you keep this in the bottom, nothing will happen. That means that elongation is very less, changes undergoing is very less, strain is very less. That means these three terms are the same. If you drop the collar without dropping, if you place from top to bottom, the strain will be very less. Suppose without dropping, if you drop collar from top to bottom, if you drop the color from the top, that means with a certain height, what happens? Deformation will be more. Deformation occurring in the bar will be more. That means that it's totally depends on height. If height will be more effect will cause. If height is more effect will be caused. If height is less effect will be caused. That means that we are dropping a load with certain height. So due to collar height, the deformation I have shown in the delta L is a deformation caused due to impact load. So that here maximum stresses induced due to impact load. Maximum stresses induced due to impact load. Sigma is equal to square root of 2E PH sigma A into L. So using by this formula we can calculate what is the maximum stress induced. So another important thing here, thermal stresses. Thermal stresses, I already said the meaning of a stresses. The meaning of a stress is the internal resistance offered by the body against deformation. Internal resistance offered by the body against deformation. Here internal resistance, why we have to develop internal resistance? Why in material developing internal resistance means it's because of temperature. It's because of temperature. Due to the effect of temperature, either drop in the temperature or rise in the temperature, whatever it may be. Either drop in the temperature or rise in the temperature, whatever it may be. Due to rise in the temperature or drop in the temperature, either drop in the temperature or rise in the temperature, nothing will happen. So that due to effect, either rise or fall, the resistance developed in the body, we can call it as a thermal resistance. That means that resistance offered by the body against deformation due to the variations in temperature. Due to the variations in temperature, then we call it as a thermal stresses. Here I have given the two conditions, that is unrestrained and restrained. Unrestrained means here one end is fixed and another end is free. Here unrestrained means here one end is fixed and another end is free. Due to the free end, in the free end it undergoes changes. I mean it undergoes elongation due to rise in the temperature. So other case I have given as restrained. Restrained means here both ends are fixed. In the restrained condition, both ends are restrained, so there is no space. There is no space for elongation. There is no space for elongation, so it shrinks. I mean, it increases the dimension in other direction. It increases in other direction. In unrestrained case, it causes tension. In restrained condition, it causes compression. So that is how to calculate the thermal stresses is very important. In this case, how to calculate the thermal stresses, it's very important thing. Here in this case, if the rod is allowed to expand freely, in this case if your rod is allowed to expand freely, the extension, how to calculate the extension? Extension dl is equal to alpha t into L. dl is equal to, it is a change in length. Here in this case we are calculating change in length. Change in length is equal to alpha TL. It's while solving the problems, it's very important, and we had, in this case we have to calculate what is the thermal stresses. For calculating the thermal stresses, we need what is the change in length. So change in length is equal to alpha into T into L, where alpha is the thermal coefficient of temperature, and T is the difference in temperature. Capital T is the difference in temperature. Capital T is the difference in temperature. Either it may be a rise, either it may be a fall, whatever it may be. Either T1 minus T2, either T2 minus T1, where T1 is the initial temperature and T2 is the final temperature. Either it may be a rise or fall, either the temperature is rising or falling, it's not a matter. Here capital T is the difference in temperature, capital T1 is the initial temperature and capital T2 is the final temperature. The difference is the capital T. And L, capital L is the initial length of the member. Capital L is the initial length of the member. If you substitute these three values, we will get as a delta L. So that then after calculating the change in length, how to calculate the compressive strain, how to calculate the strain? I already told either it may be a compression or it may be a tension. It depends on totally how the condition of the material, whether it is a restrained or unrestrained. I already told in case of unrestrained condition it causes tensile stresses, in case of restrained condition it causes compressive stresses. So that we have to calculate what is the compressive stresses, either thermal stresses, in thermal whether it is a tensile stresses or compressive stresses. So in case of before calculating the stresses, we have to calculate what is the strain. Because we know the Young's modulus of the material, what is the Young's modulus of the material. By using Young's modulus of the material, we have to calculate what is the thermal stresses. So that before calculating stresses, we have to calculate what is the compressive strain. Compressive strain is nothing but we already know the definition of a compressive strain. It is a change in length to the original length. Here I already told change in length. Change in length is what you are given alpha t into L. Your change in length, that is expansion prevented. That means that the resistance. That's all. Expansion prevented, that is alpha TL. Alpha TL divided by capital L. Alpha TL divided by capital L. Capital L and capital L get cancelled. So remaining thing is alpha T. If they ask you to calculate directly what is the compressive strain, means you can substitute directly alpha into T. If you substitute alpha is the thermal expansion, coefficient of thermal expansion, and capital T is the difference in temperature. Capital T is the difference in temperature. If you multiply by difference in temperature, if you multiply by a coefficient of thermal expansion and difference in temperature, we will directly get it as a compressive strain. By using the compressive strain and Young's modulus, we will get it as a stresses. If you multiply by strain into Young's modulus, we will get as a stress. Here I already told it's either may be a compressive strain or tensile strain. It may be a compressive strain or tensile strain. Whether the type of strain depends on what? On what condition of material. It's a condition of material. Whether condition of support. It totally depends on condition of support. It's the restrained or unrestrained. So based on that, we can classify the strains. So after calculating the strain, we have to calculate the stresses. You have given compressive stress is equal to sigma is equal to strain into Young's modulus. If we use the compressive strain, we will get compressive thermal stresses. If we use the tensile strain, we will get tensile thermal stresses. So it totally depends on how the loading condition. So here I already said whether the rise in the temperature and fall in the temperature. Suppose when bar is cooled, what happens here? T2 minus T1, because T2 minus T1, it is a fall in temperature. In the same case also in the tensile strain also already given as an example for compressive strain. In this tensile strain, here also same case, alpha into TL. Just in problem, while solving the problems, it is very important, either T1 minus or T2 or T2 minus T1. Based on that, if you take T2 minus T1, it is a tensile strain. If you take T1 minus T2, if you take T1 minus T2, it is a compressive strain. If you take T2 minus T1, it is a tensile strain. If you substitute the value of change in length to original length, we will get tensile strain, and by using this tensile strain, we can calculate what is the thermal stresses. By using this thermal stresses, generally we can take it as an expansion to the original length. That is a definition of a strain. I already told definition of a strain, change in length to original length. If you substitute change in length equation, we will get strain. What is the actual strain? By using that strain, we can calculate what are the stresses. So that here up to now we have completed the theory for all the topics. So that we can solve one simple problem. In this chapter for your syllabus, we have to solve what is the problems on the stresses, strains, and what are the cross sections of varying bars of cross section, and what is the problems on ultimate stresses and yield stresses, and we have to calculate what is the problems on composite sections, and we have to solve the problems on thermal stresses and thermal strains. Let us firstly we can solve it as from the problems on stresses. That is, we have not covered the percentage elongation and percentage reduction in the area. In the first case, we can solve problem as a given problem as a mild steel bar was tested for its tensile strength by a specimen of 12 mm diameter with a gauge length of 60 mm. Gauge length of 60 mm. Here following observations are given. The first one is final length 78 mm and final diameter as 7 mm. Yield load as 34 kilonewton and ultimate load as 61 kilonewton. This is the given data. By using this data, we have to calculate what is the yield stress and what is the ultimate stress and percentage elongation and percentage reduction in area. Here first initially you have to note down what are the data given. The first one given as the mild steel has a specimen of 12 mm diameter, that is small d is 12 mm. That is the initial diameter before testing. This is the initial diameter before testing. The second one is here given as a gauge length. Here given as a gauge length as 60 mm. Here given gauge length as a 60 mm and final length, that is L dash, final length as 78 mm. That means here length is increasing. By observing these values, we can come to conclusion that it is a tensile test. And they are given as an yield load. Yield load is 34 kilonewton. The meaning of a yield load is what? At 30 kilonewton load, the specimen is yielding, get changing and get converting into ductile. That is the meaning of an yield load. And fourthly is given as ultimate load. Ultimate load is given as 61 kilonewton. 61 kilonewton is the ultimate load. So that initially we have to calculate what? What is the first one? We have to calculate what is yield stress. What is the meaning of an yield stress? It is a stress corresponding to the yield load. We can call it as an yield stress. So that it is the yield stress is equal to yield load divided by area. Yield load already given, and we have to calculate what is the area. Here we have to calculate what is the area. We have area is equal to pi d square by 4. And given initial diameter as pi into d square, that means 12 square pi d square by 4. We will get area as 113.14 millimeter square. This is the cross sectional area for the given diameter of the bar as 12 mm. Here we will get area as 113.14. So that substitute this area in yield stress equation. Substitute area in yield stress equation. So that yield stress is equal to how much yield load is given? It's a given yield load as a 34 kilonewton. So that we are converting 34 kilonewton into Newton. That means 34,000 Newton divided by area as 113.14. 113.14. We will get as an yield stress as a 300. If you solve this expression in calculator means, we will get answer as stress as 300.61 Newton per millimeter square. 300.61 Newton millimeter square. It is an yield stress. That means that at particular this stage, stress development is 300.61 Newton per millimeter square. Then we have to calculate what is the ultimate stress. We know that ultimate is a stress corresponding to the ultimate load. We know that ultimate stress is nothing but it is a stress corresponding to the ultimate load. We have ultimate stress is equal to ultimate load divided by ultimate load divided by area. And here ultimate load given as a 61 kilonewton. Here ultimate load given as a 61 kilonewton. We are converting kilonewton into Newton. So 61,000 Newton divided by areas 113.1. 113.10 is the area. Here 113.10 as an area. So that if you solve this, we will get ultimate stress as 539.34. 539.34 Newton per millimeter square. Because here we have converted kilonewton to Newton. So here 539.34 Newton per millimeter square is the ultimate stress. Again, after calculating the ultimate stress, we have to calculate what is the percentage of elongation. What is the percentage of elongation? I already told that here it is a tensile stress automatically. So here we are applying a tensile stress. So automatically length getting increasing. So that initial length we have 60 mm. Finally, after the testing, specimen has become 78 mm. 78 mm. So that we can conclude that here specimen is getting elongating. So that we have to calculate here percentage of elongation. Percentage of elongation. I already told in the theory class that percentage of elongation is calculated by L dash minus L divided by L into 100. L dash minus L divided by L into 100. We have to calculate. This is the percentage of elongation. Here L dash is nothing but what? It is the length after specimen get tested. It is the length after specimen get testing. Length after testing the specimen. Or we can call it as a it's a final length, or we can call it as a final length, So L is the initial length. So substitute the value of L dash and L. We will get L dash as 78 mm. 78 minus 60. 78. This is the final length, and this is the 60 is the initial length. 78 minus 60 by 60 into 100. 78 minus 60 divided by 60 into 100, we will get is the percentage of elongation. If you simplify this expression, we will get percentage of elongation as 30%. This is the percentage of, that means that 30% of the bar is getting elongated due to the given loads. Is the 30% of rod getting elongating due to the given applying loads. So next step. So in the next step, we have to calculate what is the percentage reduction in area. So next step, we have to calculate what is the percentage reduction in area. Percentage reduction in area. So that A minus A dash divided by A minus A dash divided by A into 100. A minus A dash divided by A into 100, where A dash is the final cross sectional area. Final cross sectional area, and A is the initial cross sectional area. See, here length getting increasing. Here length is getting increased. So length is the longitudinal strain. Here length is the longitudinal strain, and here D is the lateral strain. So that exactly we are applying load. Perpendicular to the surface. Here exactly we are applying loads to the perpendicular to the diameter surface. That's why. So L is the longitudinal strain, and area diameter is the lateral strain. Diameter is the lateral strain. So that here length is getting increased. So exactly in opposite process, automatically diameter will be get reduced. That means area will be get reduced. So here we have to calculate what is the difference in area. That means that if you apply pi d square by 4 minus, if you use initial diameter, this is the initial area, so final area 5 d1 square divided by 4 divided by pi d square by 4. If you take 5 by 4 as a common factor, in the above case, d square minus d1 square divided by pi by 4 d square. So that 5 by 4 get cancelled. So expression will remain as d square minus d1 square minus d1 square divided by d square. D square minus d1 square divided by d square. So if you substitute the values of the diameters in this expression, d square minus d1 square divided by d square. So what is the initial diameter? Initial diameter was a 12 mm. 12 square minus 7 square. 12 square minus 7 square divided by 12 square. 12 square minus 7 square divided by 12 square into 100. That is a percentage. Into 100. Into 100, we will get percentage reduction here as 60%. 60%. That means that 60% of the cross sectional area is getting reduced due to the applied loads. So that our problem will be over. We are calculate what is the yield stress, that is the stress corresponding to the yield load. Again second step, we are calculated what is the ultimate stress. Ultimate stress nothing but it is the stress corresponding to the ultimate load. Again we are calculated what is the percentage reduction due to percentage reduction in length and percentage reduction in an area. And let us discuss our second problem. This is totally on elastic constants. You are given as a bronze specimen has a modulus of elasticity 1.2 into 10 to the power of 5 Newton per millimeter square, and the modulus of rigidity as 0.47 into 10 to the power of 5 Newton per millimeter square, and determine the Poisson's ratio of the material. It is a Poisson's ratio on the material. Here we are given as two values of an elastic constants, that is Young's modulus E is equal to 1.2 into 10 to the power of 5 Newton per millimeter square, and another one is modulus of rigidity G as 0.47 into 10 to the power of 5 Newton per millimeter square. 0.47 into 10 to the power of 5 Newton per millimeter square. In this case, we have to calculate what is the Poisson's ratio, that is mu or 1 by m. In this case, we have to calculate what is the mu, we have to calculate what is the Poisson's ratio, by using these two elastic constants. We have the relation already told in the theory class. We have an expression E is equal to, this is a relation between Young's modulus and rigidity modulus. E is equal to 2 into C into 1 plus 1 by m. E is equal to 2 into C into 1 plus 1 by m. E is equal to 2 into C into 1 plus 1 by m. So if here our intention is to calculate what? 1 by m. We have to calculate what is the 1 by m, that is called mu. We can call it 1 by m as 1 by m or mu. So we have to calculate what is the Poisson's ratio. In this expression, if you substitute the value of E, is equal to 1.2 into 10 to the power of 5 is equal to 2 into C. What is C? 0.47 into 10 to the power of 5. 0.47 into 10 to the power of 5. So 1 minus mu. 1 plus mu. If you substitute, if you modification this expression, we will get it as 1 plus 1 plus 1 by m is equal to 1 plus 1 by m is equal to 2 into 0.47 into 10 to the power of 5. 2 into 0.47 into 10 to the power of 5 divided by 1.2 into 1.2 into 10 to the power of 5. If we simplify this, we will get 1 by m is equal to 1.276 minus 1, 1.276 minus 1. So 1 by m is equal to 0.276. 1 by m is equal to 0.276. 1 by m is equal to 0.276. Here we have to understand the meaning of this value, meaning of Poisson's ratio 0.276. So 0.276 is nothing but 27.6%. 27.6% or 27.6 lateral strain is 27.6% of longitudinal strain. 27.6% of longitudinal strain. So today in this class we have discussed about what? Total strain energy. We discussed about total strain energy, resilience and modulus of resilience, proof resilience, and different types of loading conditions and different types of thermal stresses and different types of conditions, that is gradually applied loads, sudden application of loads and impact loads, and thermal stresses. There are two types we have discussed, that is unrestrained condition and restrained condition, and how to calculate. We have discussed about how to calculate the thermal stresses, thermal strains and all. In the next class we can discuss about the problems on composite sections and as well as problems on thermal stresses. In composite conditions we have to calculate how the loads will be shared by the many members, how the loads will be shared by different members, and what are the stresses developed on the different members, and also strains caused in different members. In composite sections we can discuss in that type of problems, and in second case we can discuss on the how to calculate the thermal stresses. Thank you.